Hi everybody, welcome to my 14th axial bar video. In this video I'm going to be solving the question you see here. And we're going to be finding out what's the compressive stress in this plastic if we tighten these nuts at the top by one turn. If you want to know something else about axial bars, feel free to check out any of my other axial bar videos. So before we begin this problem, we realize that it's going to be statistically indeterminate because we have a force from these two steel rods and we have a force from the plastic, and we really have only one equilibrium equation, the forces. Alright, so the first thing we want to do is draw a free body diagram of this thing. Alright, so we want to find the internal normal forces in order to find the stress in the plastic. So we find the stress in the plastic divided by the area of the plastic, we get the stress in the plastic. Alright, so let's go about finding the internal normal forces. We'll do that by making a free body diagram. Alright, now I'm going to make the free body diagram of this plate, I guess you would call it, on the top. You could make it of, these pieces of metal, but at the end of the day it's all going to be the same free body diagram. So let's just draw this out neatly. Alright, now the forces that this thing is going to feel, we want to kind of give a general direction. Because the directions. When this thing is in, some sort of final resting place, presumably it's going to move down, so the plastic's going to want to push it up. Okay, so we can say the normal force from the plastic is going to be pushing up on the plate. And the steel, presumably, is going to have stretched, so it's going to be pulling down. So we have the normal force from the steel pulling down here, normal force from the steel pulling down there. Okay, now this is not end steel by 2, end steel by 2, like it was in the previous question, because each one of these members is separate. Okay, you could say it's, n by 2, n by 2, but then you just have to make another equation that said n by 2 plus n by 2 equals, something else, and then sub it back in. No. Each one of these is a different member. Each one has a different force in there. They will happen to be the same force, but we don't need to divide it, like if it's the case where you have some sort of collar. And we'll go about some of the forces. Y equals 0. And we can find NP minus 2 and steel equals 0. So this is our first equation, and it's going to be our forces equation. Alright, so like any other statistical indeterminate problem, we need to move into the displacement to find the other unknowns. Displacement. Alright, so this step here, we just need to find the geometry of the displacement. Alright, now if you've watched my introduction to statistical indeterminacy, you might have an idea how I'm going to approach this. If you didn't, all good, we'll just do it here. So I like to imagine this one as 3 separate stages. Alright, so it's always good to draw displacement diagrams before and after. Alright, so we'll call this 1, okay, so the first instant in time. It's existing happily up there by itself before you tighten the nuts. Now you tighten the nuts, and we pretend that this piece of plastic is in here, is going to drop down the full distance that the turning of one nut goes down. Alright, and that's just going to be the pitch. Alright, the pitch is how much the nut moves down that threaded bolt if you turn it one time. Okay, so it's just going to be the amount of the pitch times 1. So it's going to move down 1 millimeter in this situation. So I'd call this position 2. But now the plastic kicks into action, and it's going to push it back up, okay? Because you've been squeezing it, and it's going to resist that. It's going to go back up to some position here. And this is the final resting place of the cap on the top. And it's from this position that we figure out our displacement relationship. Okay? So measuring everything, if you have to measure your displacement relative to something. So we can do it off the bottoms, off the tops, doesn't matter. I'll just choose the bottoms. And we can go like this piece here. And of course, the total thing, like we just discussed, is going to be the pitch. All right, I think they call it NP, times the number of turns. All right, we'll just call that N. All right, and this is going to be 1 in our case. Now this is where the plastic started. We imagined that it got compressed up to 0.2, but then it recovered and went back up to 0.3. So the final amount the plastic has compressed is this distance right here. So we'll call that delta plastic. And this piece here, we threaded it down. The steel is not feeling any stress, as we're pretending that it has no, piece of plastic there initially. We've threaded it down, then the plastic kicks in and stretches the steel back a little ways. All right, so this piece here, the amount it's stretched back, delta steel. Okay, so we can simply write an equilibrium equation here. Number of turns, or the pitch, times number of turns. 1 turn, 1 millimeter per turn. That's going to be 1 millimeter, this distance here. So in terms of meters, we would say 0.01, this is 1 millimeter, equal to delta plastic plus delta steel. Okay, there we go. This is our second equation we need. Now we can move into the force displacement relationship. And it's the one we know very well. Delta is NL over AE. Okay, now this delta P has basically this equation solved for each of those values because the displacement of the plastic is due to the properties of the plastic. And the properties of the plastic are these 4 things right here. So we can write 0.001 equals N plastic, L plastic over A plastic, E plastic plus N rod, N steel, L steel over A steel, E steel. Okay, now plugging in our numerical values. 1 equals 2 N in the plastic. Now the length of plastic, in this case, it's going to be from the initial position the plastic was. Well, the initial length of the plastic is 200 millimeters. Okay, 0.2 over the area of the plastic, the E of the plastic. So this is going to be 960 times 10 to the minus 6. All right, once again, this is millimeters squared. We want to convert it into meters squared so you don't have to do any fancy deciphering of, meganewtons per nanometer. What is that in terms of meters? No, put it all in terms of just newtons, just meters, and you'll get your answer in just newtons, and from there you can convert it on. Same thing with the Young's modulus plus N steel, length of steel. Now, in this case, the length of steel, technically it's not 0.2 because the length is always the initial position, the initial length of the piece before it starts to undergo any sort of stretching or scrunching action. So in this case, you've tightened the bolts and then it started to elongate. So it's actually 200 millimeters or 0.2 meters minus 1 millimeter. But if you think about it, it doesn't make any difference if you're going to put 0.2 or 0.199 in here. I'll just say 0.199, 0.2, not going to make a huge difference. But on the other hand, this one here, that does make a big difference. So don't say that this is 0 because once you multiply it by this big bottom denominator, that becomes a big deal. Okay, and then of course AE for this one. And equation 3 and B equals 36,000 minus N. Oh, sorry. There we go. We'll go right ahead. We plug 3 into 1. All right, now notice here we want to solve for the stress in the plastic. So if we're going to plug 3 into 1, we want to be left over with N plastic. So we solve for N steel, so we get N plastic. Alright, if you put N plastic equals something N steel, and then plugged it back in here, you would get N steel, and then you'd just be another step away from your answer. So I'm just doing this strategically. So putting 3 into 1, N plastic minus 2 times 36,000 minus N plastic equals 0. Turns out N plastic equals 24,000 newtons. Okay, and we know sigma plastic is N plastic over A plastic. That's of course 24,000 newtons over the area of the plastic. Well, that was 960 millimeters squared. And this comes out to be, converting it into megapascals right away, 25.0 MPa. Alright, so that's how you solve this particular problem. So as a quick review, we asked to find the stress in this middle plastic piece of this apparatus here. So that means you need to find the normal force in that piece and then divide it by the area of that piece. So we made a free body diagram of the lid. We realized the plastic is going to be pushing up and the steel is going to be pulling it down when it's in its final resting place. We did equilibrium equation of that. We drew out a diagram of what's happening in the displacement. We realized that the pitch times the number of turns was the sum of the two displacements. We put our displacements in terms of their components. You know, plastic displacement is due to the components of the plastic. Alright, then we just went and we solved this equation, which we know N plastic, N steel. And we have another equation, N plastic, N steel. Solved them simultaneously, strategically, so that we ended up with N plastic. And then we just realized stress is N over A. We got a final answer of 25.0 megapascals of stress in that piece of plastic. Alright, you guys, thanks so much for watching. I'll see you in my next video on axial bars.